Hello. In this lab, we investigated projectile motion by comparing real experimental data to two computational physics models, one including only gravity and the other one including both gravity and air resistance. The purpose of this lab was to analyze the motion of a real projectile using video analysis and then modeling the motion using Newton's second law. Specifically, we wanted to determine how well a gravity-only model predicts real motion and whether including air resistance significantly improved the accuracy of the model. The main result was that gravity-only model overestimated the horizontal range, while the gravity plus drag model matched the experimental trajectory much more closely. The system in this case was the rolled-up paper ball, while the sources included gravity and air resistance. The fundamental physics principles in this lab was based on Newton's second law, which states the net force acting on a system equals the mass of the system multiplied by acceleration. The gravitational force was given by F equals mg with the force facing in the negative y hat direction. Air resistance was modeled as a force proportional to the square of speed and pointing opposite the direction of motion. Here, B was a proportionality constant that depended on the object's shape and air properties. In the experimental setup, to collect data, we recorded a video of a loosely wadded paper ball thrown across the room onto the floor. The motion was two-dimensional and entirely across the camera's field of view. The mass of the paper ball was 0.005 kg, and the initial height was 0.305 meters initially, but at the point of start, when cropping the video, was 0.334 meters. Eventually, our data was cropped to start at 0.067 seconds, recalculated as 0 seconds in the data. To make the model more accurate, the x-axis was tilted by 1 degree counterclockwise to account for the camera angle. We marked the position frame by frame and obtained position versus time and velocity versus time data, allowing us to extract the experimental trajectory of the object. When developing the computational model with gravity only, we built a computational model using the velocity update and position update formulas. In this case, the F-net only countered for the gravity equation vector, which is negative m times gravity. In this case, we set B equals 0, so the drag force vector was set to 0 in this situation. With the drag force model, we modified it to include air resistance. Drag force always points opposite to the velocity vector and has a magnitude proportional to the square of the speed. If the drag force constant was set to 0, the model reduced to the gravity-only case. So in this case, we experimented with different B values to see what most accurately matched the data. In this case, we chose 0.001 as our B. When comparing all three trajectories on the same graph, originally, the drag force model wasn't lining up near the blue line, which indicated the tracker position, despite the B value placed in the code. Therefore, an error must have taken place when either collecting data or making the code. When comparing the different trajectories onto the same graph, we plotted the position x against the position y for all three. The drag force model didn't line up near the blue line, which was the tracker position as expected, despite the v value we placed in the code. Therefore, there must have been an error. Here is the corrected trajectory graph. As you can see in this situation, the tracker position and the glow script position with both gravity and the drag force included closely align with one another. This means that the experiment went successfully. The velocity we used in this situation is 1.67, 2.4, and 0 meters per second. It required adjusting our tracker position to begin at x equals 0 meters and recalculating my initial velocity. To talk about terminal velocity, which is the maximum constant speed a falling object reaches when the upward force of drag and equals the downward force of gravity. The two forces are equal to each other, therefore they cancel out, resulting in no overall force. In a projectile experiment, the object does not remain in the air long enough for the drag force to fully balance gravity. The vertical velocity doesn't level off before impact. If the object was thrown straight up in the air with the same initial speed, the total time in the air would be longer. And then the total time would be 2 initial velocity over gravity. With air resistance, the object would slow down faster on the way up and fall differently on the way down. Resistance, the object would slow down faster on the way up and fall differently on the way down. But overall, the time in the air would be longer than my original angled throw. Tracking precision, as X needed to be 0 and Y values couldn't be negative, so there must have been some miscalculation to begin with, as well as human error when estimating B could get in the way of my model. In conclusion, the lab demonstrated Newton's second law accurately describes projectile motion. The gravity-only model works for ideal situations, but in real-world situations, the motion requires air resistance.